you for joining today's OzonAction Webinar, the second session of the RefTalk series. Today we will discuss the HFOs, and we will try to give as much as possible the information about the question, will it constitute the HCFC and HFC as a long-term solution? Before we start, let me introduce myself. I'm Samira de Gobert from UNEP OzonAction Paris, where I am a member of the E-Group, and I am very pleased to be the moderator of today's webinar. Before we start the webinar, let me take a few moments to inform you that OzonAction is offering this forum to promote ozone layer protection through the use of modern technologies and to increase the global online learning and knowledge sharing. This is part of OzonAction Clearinghouse services under the Multilateral Fund for the Montreal Protocol implementation. Let me give you a few details about how today's session will run. We will be together for about 1 hour to 1 hour and a half. And for the duration of the webinar, all the microphones will be muted to avoid background sound during the presentation. However, if the participant would like to raise questions, of course you can do so. Please type your questions directly into the chat box, and if you can also indicate your name and organization and country. The webinar will be recorded and made available for the participants through the webinar platform right after the session. During the session today, we will have 4 presentations, and we will also allocate enough time for question and answer. The webinar will be facilitated by Mr. Ayman El-Kalouni, who will introduce today's topic. We are having, one of the presenters is having trouble connecting, so we hope that by the time we introduce the topic, we can be able to listen to Mr. Ayman El-Kalouni. He is the Program Officer in UNEP OzonAction for the Compliance Assistance Program in Regional Office West Asia in Bahrain. Mr. El-Kalouni joined UNEP in 2003, and he is specialized in the field of refrigeration and air conditioning. Before joining the UN, he worked for 10 years in the refrigeration industry and 4 years as technical advisor for the Egyptian Environmental Affairs Agency and for the implementation of the Montreal Protocol. He is currently responsible in the Regional Office for West Asia for the implementation of phase-out plans of ODS in the West Asia region, and is closely working with West Asian governments to eliminate the use of ozone-depleting refrigerants in different refrigeration and air conditioning, industrial and servicing sectors, as well as to combat illegal trade in ODS and ODS-based products. So Ayman will be our today's session facilitator. And now I would like to invite Ayman to introduce today's topic.
Thank you, Samira. Thank you, Samira. Good morning, good afternoon, or good evening to all of you, wherever you are. Thank you so much for joining us today, this second webinar under the title of RefTalk. Today's webinar is part of a series launched by the OzonAction Group of UNEP earlier this year, specialized to highlight the latest development in the industry of refrigerants and introduce more information to different stakeholders, industry, government, and specialized experts in the field about where we stand in terms of the newly developed or deployed refrigerants being promoted over the last few years as a long-term substitute for ozone-depleting substances, and eventually as well for the greenhouse gases responsible for the climate change. Our today's session, as I mentioned, will be focusing on the HFO, which is the newest member to the family of refrigerant, being introduced most recently over the last 5 years only. It made a breakthrough in the MAC for mobile air conditioning industry, notable breakthrough, and today we are trying to understand whether. I would like to highlight in the beginning that today's presentations and points of view are not necessarily fruitful webinar. I would like to reiterate what my colleague Samira mentioned for a while, that we have a limited time to conclude this webinar in not more than 1.5 hours. We understand that we already starting a little bit late, but we will try to stick with the time as much as possible, and given the number of audience attending this webinar, we would like to leave an adequate time for the questions and answers at the end. I would like to kindly ask all the attendees to keep note of their questions, and I would like also to kindly ask them to limit their questions to 1 or 2 questions maximum at once at the end of the fourth presentation today. We will be starting the first presentation. We should have been starting the first presentation with Dr. Dennis Claudic. However, we are facing difficulties to connect him, and we're facing this problem with SPC. So meanwhile, we will be proceeding with the second presentation directly, which is being introduced by Mr. Mark Hutz from Honeywell Fluorine Products. Mr. Stutz is the global leader for refrigerant technology with Honeywell for environmental friendly refrigerant. His extensive background includes nearly 40 years of experience in the research, development, and design of refrigeration, cooling, energy, and heat transfer systems, in addition to the vapor compression technology. Conducted research and development on other technologies such as reciprocal cooling, absorption, heat pipe technologies, stirring, and polymer recycling. Mr. Stutz received a master's degree in mechanical engineering from Union College and bachelor's degree from City College of New York. He is an active member of ASHRAE and Society of Automotive Engineers as well. His presentation today will be evaluation of low-GWP velocity.
Thank you. All right. Can everybody? Hopefully, everybody can see the presentation. And thank you for the very nice introduction. We'll turn to the second slide here and just briefly go through the agenda, followed by a very short introduction. We'll discuss some of the evaluation results of low global warming alternatives to R410A, both from a performance and lubricant warming alternatives for high ambient temperatures. And both simulation results and more recently we've done some testing as well, and we'll share both. Followed by some conclusions. So, just by way of introduction here, we've in addition to the single molecule refrigerants such as HFO 1234YF and 1234ZE. We developed a series of blends to enable the use of these refrigerants in applications other than 134A applications or lower pressure applications. So we developed actually a series of two series of blends. One that is reduced in GWP. However, these are still non-flammable options, and we call that an N series. And then even lower GWP series, the L series, that is mildly flammable. And all the L series would be classified as an A2L refrigerant, so it's the lowest flammability classification. So we see we have an N13, which is a non-flammable 134A replacement we used in chillers and medium temperature refrigeration, followed by replacements for 22, both an N20 and an L20. The L20 actually has a GWP below 300. And then the 404A replacements, the N40 and L40, and finally the 14A replacement. Just to talk a little bit about some of the evaluations that were performed, we did an evaluation of the L41 in a mini split or a rack system at our Honeywell test facility in Shanghai, China. And basically it was a fairly standard unit, 3.6 kilowatt cooling capacity, and test conditions following the ISO standard 5151 as shown on this graph, on this table. For L41, we had to use a compressor with slightly larger displacement, about 10-11% larger displacement. And you see all the conditions. For the interest of time, I won't go through all those. And as far as the performance results, we saw very good performance as expected in the standard compressor, these larger displacement compressor in. We were able to match the capacity and still have an increase in the COP or efficiency. And that was in cooling. In heating, very similar results. Able to make up to by and large, make up to the shortfall in capacity with the original compressor, and still have an increase in heating COP over that of 410A. So basically, performance was very good. Discharge temperatures were slightly higher with L41 than 410A, but well within maximum permissible, and well below that of using pure R32. We also tested it in our facility here in Buffalo, New York, in a typical ducted split system. And again, very good performance, cooling efficiency at 35-degree ambient. Would match that of 410A with slightly higher capacity with the slightly larger compressor displacement. Heating performance both at the radiant condition and at the low ambient condition of -8 matched or exceeded that of 410A. And all this with discharge temperatures that were below the maximum permissible, and again below that of R32. As far as the lubricant compatibility with this material, the overall assumption was that most systems require the oil and refrigerant to be miscible, in other words, one layer. And there are difficulties working with oils that are not admissible because it could lead to oil logging in various parts of the system and potentially poor oil return to the compressor. And we see here that with L41, the miscibility range is actually increased beyond that of 410A. You see the diagram on the lower right-hand side is the miscibility diagram for L41 with a relatively standard POE and ISO 68 POE. And that's in contrast to R32, where basically it's immiscible over the most of the operating range and really would require new oil to be able to use effectively with that particular refrigerant. And then moving on to the topic of high ambient applications. And the overall issue at running at high ambient is basically how close are you getting to the critical point of the refrigerant that you're currently using. And with R22, the difference between the typical condensation temperature, even at higher ambient, is still significant between that and the critical temperature. However, if you move on to higher pressure refrigerants such as 410A, you see that the differences between the condensation temperature and the critical become much smaller, and hence this is brought out here in just a simple thermodynamic analysis of various options, R22, R410A, and R32 more or less as baseline, and then we added our L41 or L20 and N20. And you see the general trend here on the lines that the medium pressure fluids like R22 and L20 tend to deviate much less at these high ambient temperatures than the higher pressure refrigerants like 410A and 32. And you see that the performance at the 46 degree point that L20 with its critical temperature very close to that of R22 performs quite well, both in capacity and efficiency relative to that of R22. And then we move to the next slide here, and basically this is a simulation. It's a detailed simulation of a mini split. We have a detailed system model that looks at all the heat exchanger performance as well as the compressor performance and the rest of the system to predict performance, and usually it matches system data very well. And again, we're looking at the deviation between typical ambient temperatures at design of 35 degrees C relative to that at 46 degrees. And we see the deviation here as we go up in temperature for some of the higher pressure refrigerants are dropping off a little more dramatically than that of the medium pressure C. Basically maintaining the capacity and efficiency of R22. And even at peak conditions of 52, very high temperature, we're able to keep up fairly well with R22. And again, we're seeing more of a difference with the higher pressure refrigerants. Not that systems couldn't be designed for that, but it would take greater heat exchange area in order to make up for that loss in performance. So we feel that the L20 with its low GWP of under 300 and very good performance is a good candidate to be used especially in systems that have been designed for R22 and can handle the very mild flammability of this material. This is a more recent data that we took on our system that was modeled in the previous slide. We went back into our laboratory and did an evaluation, experimental evaluation, and compared the L20 against R22. and basically looking at the three conditions, the T1, the T3, and the extreme condition of 52 degrees. And we see the comparison capacity-wise for L20 at all conditions was maintained of that of R22. Efficiency was very close, within 1 or 2 percentage points, basically within experimental uncertainty. The mass flow was a bit lower, so there is, even further room for optimization, and discharge temperatures were maintained at adequate levels. Now, we did do some optimization of circuitry, actually both in the simulation and in this experimental evaluation, to take advantage of the temperature glide of the L20 interior. And then finally, the summary, we basically developed a family of low global warming refrigerants, replaced most common refrigerants. We feel that the latest 410A replacement offers very comparable performance to 410A, but avoids the high discharge temperature and permissibility of R32. And we are encouraged by the more recent work we've been doing on our L20 as a 22 replacement in high ambient applications. And we're continuing to work closely with industry to evaluate all these products in a multitude of stationary air conditioning applications, and we feel that the HFO and HFO blends should be considered as part of the transition away from higher GWP refrigerants.
Yeah. We can't hear you anymore.
Oh, yes, sorry. I was just trying to get back to the original screen here.
You still have one last slide, I guess?
No, that was it. I'm sorry.
Okay. Thank you very much for your presentation, and I'm very pleased to inform that we were able to connect Dr. Denis Claudic, who will be our next speaker.
Yes. Do you hear me?
Yes, we can hear you, Dr. Claudic. So let me introduce you to our participants. Dr. Denis Claudic is president of RefTalk-2, which is an R&D company that he created in 2011. He is working downstream research laboratories for the development of technologies that have been proven at the laboratory scale. Dr. Claudic is an emeritus research director of thermodynamics of energy systems and the core of his competence. He is author and co-author of more than 150 international conference papers and of more than 30 peer-reviewed articles. He is co-laureate of the 2007 Nobel Prize for its contribution to IPCC. He is member of Académie des Technologies since November 2010 and a member of the ANR Scientific Council on Energy, vice president of AFCE, which is the Association of Refrigerant Choice, ASHRAE member and chair of 2 standard committees, and a member of the Technical Option Committee of UNEP on refrigerants. Dr. Claudic will introduce the refrigerant choice criteria for the different refrigeration and air conditioning sectors and try to tell us more on what could be the best candidates. Dr. Claudic, we are listening to you.
Thank you very much for the nice introduction. So
I think you can see now my chart, my imaging. Myself, I don't see anything, but I go on.
Yeah, so if you just click on the share my file, please.
Okay. Excuse me. I don't see you anymore.
Okay, to gain time, we can offer to flip through your PowerPoint presentation from here, from our end.
Okay, good.
Okay.
So first thing, we go to the contents. I will go quickly through that in order to, you hear me?
Time, we can try, and then if it doesn't work, then we are happy to share the presentation from our end.
Yes. What I don't understand, I have something new on my screen, but well. One key issue is to take into account the size of refrigerant. You have it? Yeah, go on.
Dr. Glodik, we cannot see your PowerPoint presentation. Can you please click on share my desktop and open the PowerPoint presentation?
Yes, but the issue is that I hear you, but I don't see anymore the OzonAction website except the very generic thing. That's my issue.
Dr. Glodik, I think that we are going to flip through your presentation.
Yes, please.
From our end.
Do it. So we are in slide number 2.
Please let me open it first. Give me 1 second.
Oh, I see you now.
Okay. So we are ready now. Please go ahead.
Yes, now I see you. Then we go to the next slide, number 2. And then the next one, yes, that is second one. Okay. One thing to stress is that in order to understand what could be the future, we need first to have a clear view of the bank of refrigerant. That's one of the key points. Secondly, we will go quickly through the different applications where CO2, ammonia, and HCs have been used, and we will go through the new unsaturated HFCs, also called HFOs, which is the topic of the day. And I will take different examples for different applications, and then we will see what could be the possible replacement for 404A, 410A, and also, of course, R22. Next one, please. Number 3, yes. So, these simulations, first, up to 2006, that was based on inventories made by my previous Center of Energy Studies. Then we make a projection based on different assumptions. The key point here is to see that in 2020 we will have about 4 million metric tons of refrigerant banked in the different applications. And the other part of the slide shows that the 3 main applications are first, nearly 50% in stationary air conditioning, then commercial refrigeration, then mobile air conditioning. Next, please. So, if the new introduction of CO2, which was an old refrigerant used in the beginning of the 20th century, and the new application is mainly based on low temperature application with a condensation of a low temperature also, and it's an option which is taken into account and installed in many large food industries as well as large supermarkets. In Japan, we had the success of the so-called EcoCute program with about 5 million equipment using the CO2 as a transcritical fluid. And then we have also an uptake in Northern Europe, so-called cold climate, for a full so-called transcritical cycle. Next, please. Ammonia. Ammonia, I should say, is an important refrigerant used since the beginning and increasing its market share. But we cannot say that we have a significant uptake, even if it is important, in the food industry. In terms of new application, they have been limited, and we can find them for some reciprocating chillers and also in supermarkets. But due to toxicity and safety issues, it's mainly used in an industrial context. Please, next. So, hydrocarbons. Hydrocarbons has been really successful as of 1992 in Europe for domestic refrigeration. There is also a new application since more than 10 years in small commercial refrigeration, but what is constant for all hydrocarbons application is that the refrigerant charge should be limited. Even when taking the most open, I should say, standard for that, we will have something in the range of 1.5 kilogram maximum, depending, of course, of the volume of the room. Hydrocarbons also are used in industrial context very differently, in refineries, for example, but in terms of general use where people are living, we have a limitation due to the flammability, of course. Next, please. So, of course, when one thing is missing in the slide, but what is important to show is that under the 10 orders in green, we have the uptake of HCs in domestic refrigeration, and what we should have seen on the right part was, of course, the dramatic effect in terms of limitation of CO2 equivalent emission. Next. So, now we go to the proper issue of the discussion. First of all, we have now a molecule, and the interest of that is that those molecules have a very short lifetime. So we have 1234YF, 1234ZE, 1233ZE. Excuse me. One thing which is interesting is that 1233ZE is an unsaturated HCFC, but due to the very short lifetime, I think this molecule will begin to be a new option, which is, I should say, a kind of paradox when applying the Montreal Protocol. And all those substances can be blended with HFC, with relatively low GWP as R32, R132A, and even R134A. So we will see what are the options and the proposal coming now. Next, please. So, 134YF definitively is a candidate to replace R134A because of the properties are very similar. Since at least now 8 years, we have on the table the proposal to replace R134A by 1234YF in mobile air conditioning. Next, please. And we have made a simulation last year for a study for the European Commission, and clearly, taking into account the uptake of 1234YF in Europe, you see on the two charts the very strong effect in, say, the next 20 years, taking into account the introduction for all new platforms in mobile air conditioning. So it's the same story as we have seen for isobutane for domestic refrigeration, but with a much stronger impact in terms of metric tons and tons of CO2 equivalent, with a very low GWP. Within 15 to 20 years, we have a total different picture of impact in terms of CO2 equivalent. Next, please. So, 1234ZE is a molecule which is used as a blowing agent for foams, and it's produced in large quantities and introduced 1234ZE as a replacement for R134A in large chillers. To be noticed also, even if Rankine organic cycles are a small application for now, this is a refrigerant of interest for this application. Next, please. 1233ZD, in fact, is also used in foam application and is seen as a very efficient refrigerant to replace R123. And it's also a molecule of interest for high temperatures organic Rankine cycles in the range of 200 degrees C. Next, please. So, what are the candidates? I have left open the list, and I have taken into account the molecules which are known and which have been tested, especially in the HRI program. I think we will have a presentation on that. So, L40 is still the name of the company because I don't think they have a national name At least I don't know it. So interestingly enough, it's a blend with a GWP around 300. So we will see if 300 is a level which is considered as low or relatively low. The interest of that it can replace fluorophoray with, more than 15 times less CO2 impact compared to fluorophoray. Next, please. So a bit more candidates on this one to replace Fortenay. Fortenay is a quite important refrigerant for stationary air conditioning, and we have a lot of discussion for experts and for large companies, large global companies producing those AC systems. If you go to blends, until now they have smaller refrigeration capacity compared to Fortenay, or to use directly HFC 32. GWP is around 700, and also nobody knows if this level 700 is considered as too high or not. Next, please. And then we have also candidates to go directly from R22 to low GWP. We have as candidates those, I should say, 3 low GWP HFC, unsaturated HFC, and some low GWP HFCs. Next, please. So, as a conclusion, I think that the trend for the next 20 years is clearly to go to low GWP refrigerants. Definitively, I think that fluorophoray and even Fortenay are being used in their last years. CO2, ammonia, hydrocarbons have a share of the new and the market since 1992, but they have inherent limitations, and that is the reason why I think that we will have room for new refrigerants, unsaturated HFCs, and also blends of those unsaturated HFCs with low GWP HFCs. Something very difficult to predict is what will be the shares. The feeling I have that mobile air conditioning system as well as stationary air conditioning system are, I should say, global markets, and so usually companies like to use global refrigerant, easy to find everywhere. For commercial refrigeration, it's a bit different. You can have local solutions because many of those systems are not exported. But we have to take into account that condensing unit is a very large application, and also condensing units welcome, global options. So that is my first conclusion. Thank you.
Thank you, Dr. Claudic, for this comprehensive presentation. And now I would like to take just 1 second before we move to next presenters to inform the participants that they can send their questions to the panelists through the chat box. Please type in your question and kindly indicate your name, organization, and or country. Thank you. And now I would like to invite Ms. Barbara Minor and Dr. Thomas Legg. We will listen to a joint presentation. They will speak respectively about an update on DuPont low-GWP HFO-based technologies for static air conditioning and refrigeration. So I open the floor first to Ms. Minor, and then we listen to Dr. Tomasek.
Not muted.
I'm listening to you.
Can you hear me?
Yes.
Okay, great. And can you see the slides?
Yes.
Okay, great. Well, thank you for the opportunity to speak with you today to give you an update on DuPont low-GWP HFO technologies. I'll be talking about our fluids for refrigeration, and my colleague, Dr. Tom Leck, will be talking about air conditioning. And the products that we'll be sharing with you today were formulated solely by DuPont, and some of the data we're presenting we developed jointly in collaboration with OEMs, with retailers, and some of our academic partners, so we'd like to acknowledge their contribution. So we'll briefly discuss why HFOs to try and address the question that was posed for the seminar. We'll talk a little bit about the DuPont Opteon refrigerants that we've developed, and then I'll speak about alternatives to 134A and 404A, and then Tom will discuss 22 and 410A alternatives, and then we'll finish with a summary. So when we ask the question, will HFOs fit into a low-GWP future, and when you think about the choice of refrigerants for a given application in a different region, there are many different considerations to keep in mind, and what we call looking at the balance of properties for each refrigerant and where it will be used. And the things to consider are at the top the environmental sustainability, the safety of the refrigerant, what are its flammability and toxicity characteristics. And then on the left, you need to look at the performance of the refrigerant in a system, what is its energy efficiency and capacity. How does it perform at high ambient conditions, for example? And then over on the right, what is the cost to use the refrigerant? And not only the first cost of the refrigerant or the system itself, but what is the cost over the lifetime of the system, the operating cost, and the total cost to use. So when we look at HFOs, how will they fit in? Well, we do believe they have an optimum balance of properties. The pure fluids, as Denny Kodik mentioned, have very low GWP, usually less than 10. And when you blend them with HFCs, they can be anywhere from 50 to 99% lower than the current HFCs. So a dramatic improvement. But they also have favorable climate characteristics in the system when you look at something like life cycle climate performance and the climate contribution over the life of the system. The performance of HFOs and their blends are comparable in capacity and efficiency to the current HFC technology, and we'll be showing this later. The safety, they're both non-flammable and mildly flammable options, and they do have an attractive total cost of ownership. They're low cost to use. The transition will be smooth because the performance can match the current HFC product. So the Opteon refrigerants that have been developed do have this balance of properties. There are two classes of refrigerants, you'll call it, one non-flammable and one mildly flammable. The non-flammable options you can see have been developed to replace the current refrigerants shown on the left, 134A, 404A, etc. And then the mildly flammable options have significantly lower GWP, but then you need to take a look at codes and standards and what limitations there might be in a given application to use a mildly flammable refrigerant. So I'll begin by talking about some of the options to replace current refrigerants in refrigeration applications. Three candidates I'll discuss today. One is called XT10, and that's a replacement for 134A. It's not non-flammable. It has a GWP of about 600, and it's about 55% lower than 134A. And the most attractive option for this candidate has been to replace 134A in medium temperature hybrid cascade supermarket systems, where you can use 134A transitioning to XT10 in medium temp and cascade to CO2 in low temp. There are two R404A alternatives. The first is DR7, which is a mildly flammable formulation with a GWP of about 250, which is 94% lower than 404A. This is suitable for the smaller charge 404A systems because of its flammability, such as condensing units, and again, the charge may be somewhat restricted due to codes and standards. DR33 is a 404A alternative which is non-flammable, so it could be used in existing systems, and it has a GWP of about 1400, which is 65% lower than 404A. So now I'll share some performance data on these refrigerants. For XT10, we do have a field evaluation. I'll share in temp and CO2 and low temp. This system has been running for 2 years. So we removed the 134A from the system and simply replaced it with XT10 with just a minor TXV adjustment and no other changes to the system. And this chart shows the overall summary performance. On the left, the blue bars is the energy use of the original 404A system, and then the Cascade 134A and Cascade XT10 systems. You can see the energy consumption is a little bit better for these Cascade systems, so that's an improvement. And then when you look at the total equivalent warming impact, the climate contribution estimated over a 14-year life of the system, you can see a significant reduction in the warming impact at TWE, at least 50% for 134A, and then an even improved reduction when you replace 134A with a lower GWP XT10. For the 404A alternatives, DR7 and DR33, we first tested them in a recent freezer that was originally designed for 404A. This is a straight drop-in test. We just made minor adjustments to the TXV to adjust for superheat. We tested at 3 ambient conditions shown on the chart. DR7 energy consumption was 3 to 8% lower than 404A, and DR33 energy consumption was equivalent to 4% lower than 404A, and all the other operating parameters in the system were similar. We then tested DR33 in a condensing unit with a display case. You can see the open case here on the left, which we filled with a load to test under standard industry conditions. Again, this is a drop-in test with only minor TXV adjustments. We tested at 2 ambient conditions, and then we also tested the system at medium temp and low temp conditions. The energy consumption was about 3 to 4% lower at the low temp conditions, and about 8 to 12% lower at medium temp conditions for DR33 compared to 404A, and all the other operating parameters were again similar. So this shows that all these candidates can be good direct replacements for either 134A or for 404A. And now I'll move over to Tom, who will talk about air conditioning.
Okay, thank you, Barbara, and thank you to the participants and organizers for this opportunity. So let's be clear, we are transitioning now from the discussion of refrigeration to a discussion of stationary air conditioning refrigerants. So let's start with this review. The CFCs, I think we all know, were developed around 1930, and the HCFCs came along about a decade later. R22, because of its very robust properties, became the fluid of choice for many applications and most stationary air conditioning. However, as a result of the discovery of stratospheric ozone depletion and subsequent ratification of the Montreal Protocol, actions were started to phase out the use of ozone-depleting substances. So for much of the stationary air conditioning market, R22 has been replaced largely by 410A and also other HFCs like 407C. However, it has been recognized that because of the low critical temperature of R410A, it has not been well suited for use in very hot climates. So R22, because of its higher critical temperature and better hot climate performance, has remained in use in many parts of the world. Research continues to identify better refrigerants for stationary air conditioning, good for all conditions, and now that we have HFOs in our toolkit. We're developing formulations based on HFO molecules and blends of HFO with HFCs to provide new options that show a lot of potential for stationary air conditioning. When selecting or designing a new refrigerant gas, there are a lot of considerations that come into play. The properties that most manufacturers point to are these. First, the environmental sustainability. That's why we're having this webinar today, and that's why refrigerant discussion has been so important lately. We want low direct global warming impact from the refrigerants, and we need good energy efficiency, that is to say, a good life cycle climate performance, so that the overall carbon impact and carbon footprint is minimized. It goes without saying that the refrigerants need to be safe to manufacture, safe for manufacturing of air conditioners and refrigeration systems, so low toxicity, manageable flammability are good parts of that. And of course, the highest possible energy efficiency is necessary to minimize the carbon impact and minimize the life cycle impact. Now, the nice to have is compatible with existing technology. A new fluid that works with existing materials of construction, existing lubricants, existing polymers and hoses and valves and gaskets is very desirable. It makes for a less expensive and less time-consuming transition to use the new fluid. And finally, refrigeration capacity is important, but not the most important, because by changing compressor sizes and changing pumping rates, one can compensate within a limited range for changes in capacity. Now, this chart is similar to the one that Barbara showed. This highlights candidates that we are developing and evaluating for air conditioning specifically. And again, on the left column, we see that we're replacing some of the legacy refrigerants listed here. Most of these are relatively high GWP or are ozone depleters or both. And you see the columns on the right. We group these into non-flammable ASHRAE Class 1 compounds and mildly flammable, the ASHRAE Class 2L. So we have the Opteon XP10, which on air conditioning is used primarily in centrifugal chillers and medium pressure chillers. DR91 is a replacement for R22. It has a similar capacity to R22, is non-flammable, and in order to keep that non-flammable property, the GWP is higher. It's approaching 1,000. And then lastly, DR2. DR2 is an HFO. It's not an HCFO. It is not 1233ZD. It's a unique HFO molecule that has shown very good properties for low-pressure chillers, but also very good high-temperature properties. A lot of options for organic Rankine cycles, high-temperature heat pumps, or the heat recovery fluid. And then finally, on the mildly flammable group, we have Opteon YS with 134A properties, and DR5, which is a 410A replacement. Now let me be a little more specific in talking about these. To describe them, I like this format. This is a plot of refrigeration capacity versus the direct global warming potential. And in this chart, capacity is normalized to that of R410A. R410A is 100%. The other candidates' capacity is scaled to that, and you can see how the relative GWP compares. And also in this format, figures outlined in red indicate the mildly Class 2L flammability. Figures outlined in black are non-flammable, and the color indicates the relative efficiency or COP relative to 410A. So adding in the new candidates, first near the upper left is DR5, has capacity very similar to R410A, and I'll say a little bit more about that. But what's most notable is the GWP is 75% less than 410A. So this is a candidate that has shown good prospects for use in systems designed for 410A. DR91 is in the center, non-flammable, nearly half, not quite half the GWP of R22, certainly less than half the GWP of 410A, non-flammable, and capacity in the range of R22. And then near the bottom center, XP10, better than the two. So these are based on theoretical cycle calculations, thermodynamic properties plugged into a computer model of refrigeration cycles. Let's go on to some actual system testing and actual performance data. First of all, DR5 has been evaluated in a large number of different manufacturers, different models, and different sizes of room air conditioner heat pump systems, the ductless or mini-split style. And what's interesting is as we go into different systems, sometimes the capacity would be a little more than 410A, sometimes a little less than 410A, and I think it depends on pressure drop in the system and specific system parameters. The capacity is close enough that with an inverter drive variable speed compressor, fine-tuning the compressor speed allows us to exactly match the capacity of 410A, so we can get good measurements of the energy efficiency, the COP. In these tests, we've seen that the annual performance factor, which is a climate-adjusted, seasonally adjusted heating and cooling energy efficiency, is better than 410A. And the life cycle performance, the LCCP, averages about 24% better than 410A. So these are very encouraging results. In ducted systems, the U.S. type, larger ducted systems, here's a typical set of results over a range from very high temperature, high ambient conditions for air conditioning and to very low conditions, very low temperature conditions for heating. We get a range of COPs up to 7% better in cooling and up to 22% better COP than 410A in the heating modes. Capacity, again, varies depending on the ambient temperature, but in the worst case, very low temperature for heating capacity was 10% less than 410A, and the volumetric compressor efficiency was about 4% better than 410A. Now this data was presented by Professor Lorenzo Kremesky of the Oklahoma State University, and there are similar results that have been presented as parts of the AHRI AREP low-GWP evaluation program. So quite a lot of published data available. So recapping a little bit here, this chart just compares overall legacy refrigerants 410A and R22 with candidates R32 and HFO blends DR5 and DR91. Again, DR5 is a good replacement for 410A. DR91 shows good potential to replace R22, particularly at high ambient temperatures, hot climate temperatures. You see the critical temperature of DR91 is about 86, not as high as R22, but certainly higher than 410A or R32 or DR5. And that higher critical temperature and the wider pressure enthalpy dome gives it good high end. Now, there is not any single refrigerant, there has never been any single refrigerant that's good for every cooling application. that HFOs will play a key role in the future of refrigeration and air conditioning, particularly as the industry drives to lower global warming potentials and higher energy efficiencies. The HFO-based refrigerants give the best balance of environmental sustainability, energy performance, safety, and total cost of ownership because they are similar, have similar properties to the legacy refrigerants, and are easily used in existing supermarket refrigeration designs, condensing units. There are options for medium pressure and low pressure centrifugal chillers and other chillers as well. We have good options for stationary air conditioning, for heat pumps and very high temperature heat pumps. Good performance options for high ambient temperature regions, and the DR2 has shown good promise for renewable energy storage and energy recovery. So in conclusion to the theme of this webinar, the data shows that HFO-based refrigerants will be an essential part of a cost-effective transition to a low GWP future state. So thank you very much, and that's the end of my presentation.
Thank you so much, Dr. Thomas Legg and Ms. Barbara Minor, for this very interesting and detailed presentation. I would like to take a moment before we listen to our last presenter to introduce you to our participants. So Ms. Barbara Minor joined DuPont company in 1981 as a chemical engineer. She is currently with DuPont Fluoro Products and is an engineering fellow for the DuPont refrigerant business. She has been in the refrigerant industry for over 19 years and has developed new refrigerants for stationary and automotive air conditioning. She holds over 90 U.S. patents for refrigerant, cleaning agent, and aerosol propellant, as well as several publications in the field. She is an active member sorry, a little technical problem. Barbara is an active member of ASHRAE and is past chair of TC31 refrigerants and secondary coolants. She is also a member of the Air Conditioning, Heating and Refrigeration Institute, serving on the AHRI Steering Committee and Research and Technology Committee. Dr. Thomas Legg as well, he is a senior principal investigator, new refrigerant development at DuPont Fluorochemicals. He has 34 years of R&D and technical work at the DuPont laboratories. He has worked in the refrigeration, lubricants, fluoration, and he joined the DuPont Refrigerant Technology Organization in 1991 and worked on technical issues necessary to bring non-ozone depleting refrigerants to the commercial market. For the past 7 years, he has been working with fluoroolefin refrigerant compositions with goals of identifying more environmentally sustainable refrigerants for use in stationary AC and refrigeration work, and evaluation of fluids for high temperature energy recovery applications. Dr. Legg received his PhD from the University of Illinois for research to educate mechanism and quantify reaction rates of ozone depletion by fluorine and hydroxyl-free radicals in the stratosphere related to leakage of CFC and HCFC refrigerants. I would like now also to take one moment to remind the participants that we receive now the questions. So please, if you have any questions for our panelists, you can type them into the chat box. And after the last presentation, we will address your questions. I'm happy now to introduce Dr. Karim Amran. Hello, Dr. Amran.
Yes, I'm online.
Okay, thank you. So I'd like to take a moment to introduce you to our participants. So Dr. Karim Amran is the Vice President, Regulatory and Research Air Conditioning, Heating and Refrigeration Institute. He is also the Vice President of Regulatory and Research at the Air Conditioning Heating and Refrigeration Institute, and he manages the industry cooperative research program and is responsible for the development and implementation of AHRI's regulatory policy. Dr. Amran has over 25 years of experience in the air conditioning and refrigeration industry. He is a member of the American Society of Heating, Refrigeration, and Air Conditioning Engineers, known as ASHRAE, the International Institute of Refrigeration, the IIR, and the American Society of Mechanical Engineers, ASME. The topic of Dr. Amran's presentation will be an overview of AHRI research program on low-GWP
Start, but it's hopefully be able to see my
so, and then you select the document you would like to share with us.
Yeah, when I click on share my desktop, there's nothing that comes up. That's interesting because we tried it before, but let's see if I...
Okay, try once again, and if there is any problem, then please let me know. I can try to open your presentation from our end.
Okay. I'm trying. Okay, hold on a minute.
Okay, please.
Do you see it or not right now?
Not for the moment.
Not for the moment, yeah. Yeah. When I click on share my desktop, somehow nothing happened. And so...
Okay, hold on 1 second. Let me try something, please. Excuse me. Okay, please retry again.
Maybe now it will work.
Yes.
Okay, hold on a minute. Do you see it?
Not now. Not yet. Not yet.
Yeah.
Okay.
Okay, now, okay, hold on. Okay, yes. All right.
Yes. Now we can see it.
Okay, good. Excellent. All right, very good.
Yeah.
So,
Fine.
all right, very good. All right, thank you very much, and thank you for the opportunity to speak today. I'm Karim Amran, and I work for the Air Conditioning, Heating and Refrigeration Institute. HRI is a trade association representing manufacturers of heating, air conditioning, refrigeration, and water heating products. We are the result of a merger between two trade associations, ARI, the Air Conditioning and Refrigeration Institute, and Gamma, the Gas Appliance Manufacturers Association. And so we've been, at least as ARI many years ago, been involved in research on refrigerants and other topics of interest to the industry for many, many years. And in this particular case, I'm going to give you a brief overview, in particular on one of the programs we started about 2 years ago, which is to look at low-GWP alternative refrigerant evaluation program, the low-GWP era program that several presenters mentioned this morning. So I'm going to skip a couple of slides because because of time. But as you all know, the industry is going through another transition. We went to the phase out of CFCs and HCFCs in the U.S. Just recently, and now we are talking about finding solution to add to high global warming refrigerants. But it's very important, and Barbara mentioned that in her presentation, when we look at choosing a refrigerant, that we look at several factors, not just one factor. A lot of discussion about GWP, and yes, GWP is very important when we look at refrigerants, but at the same time, we need to look at safety, the contribution to climate change of an air conditioner. The contribution to climate change is mostly due to the energy consumption of the product, not the GWP of the refrigerant. 90% plus is due to the energy consumption. So energy efficiency is key here when selecting alternative refrigerants. But of course, economics have to play as well. And there are other factors such as, operating pressures, lubricants, material compatibility is very important, and flammability, which is related to safety. So we need to keep that in mind when we look at choosing alternative refrigerants. Now, as far as the HRI and what we've been doing on low GWP refrigerants, I mean, we've done several research projects. I'm listing on this slide several projects that we've completed recently. I'm not going to go through them because there is no time to go through them, but I'm just listing what we've done. And those reports, by the way, are available for free on our website for downloads. So those who are interested can look them up. But basically, we looked at several things, such as, for example, looking at regulations that are preventing the use of certain flammable refrigerants. We looked at thermal and chemical stability of low-GWP refrigerants, risk assessment of some of the 2L flammable refrigerants, 2L being the ASHRAE new classification for mildly flammable refrigerants, by ASHRAE 34, standard 34. So just to give you an idea, I mean, and those reports, as I said, can be looked at and downloaded from our website. We're going to be starting a few more research projects in the coming weeks and months, looking at risk assessment on the refrigeration system using A2L refrigerants, but also doing some material compatibility work as well. But I'm going to be focusing my talk on the last bullet on the slide, which is the low GWP alternative refrigerant evaluation program that we started about 2 years ago. And that program is really, the intent of it is to identify alternative refrigerant to high global warming potential refrigerants. And we started the program at the request of OEMs, that there was a need to assess what was needed to do. And of course, to help accelerate industry response to environmental challenges. And most importantly also is to avoid the duplicative work, because at that time, about two and a half years ago, manufacturers already started testing and said, well, instead of doing same kind of work, why don't we spread out the workload so at least we can test more, and that's how we started the program. But one key important thing as far as this program is concerned, the program is not going to prioritize the refrigerants. We're not going to come up with a list of this is our number one choice, this is our number two choice. No, that's not the intent. The intent is to test and present the results in a consistent manner, to make the results available to anybody to look at, and it's going to be up to the industry to pick what they believe, manufacturers what they believe is more appropriate. So we are about 2.5 years through the program. We started back in March of 2011. And at the end, although we have already made reports available to the public on our website, and at the end of the presentation, I'll have a link for those who are interested in looking at those reports. So we have about 22 reports already available on our website, and we intend to complete at least first round of testing in the third quarter of this year and make everything available on our website by that time. So what we did is that we solicited the industry for a list of low-GWP refrigerant candidates. We received that list from OEMs, from chemical producers. And then we solicited OEMs for test plans. So basically, we invited OEMs to participate in the program. OEM being, by the way, in the U.S., where AHRI is, but also overseas as well. We have testing companies from Asia and from Europe also involved in this program. So it's not just a U.S. program, it's a global program. So those testing companies proposed test plans according to their individual interests. So we didn't force anybody to test anything. It was them coming to us and, yeah, I'm interested in testing that refrigerant in that application. And that's how we framed the program. Now, the testing companies then are directly report the result to a committee, to an HRI committee. It's the HRI low-GWP AREP technical committee. This committee is in charge of reviewing the report, making sure that the information contained is appropriate and is consistent with the reporting requirements. And then this committee approves the report, and then when they are approved, they are posted on our website. So as far as the candidates, I'm going to go briefly, that's about 3 slides that list what they are. In this case, for example, you can see the baseline refrigerant being R134A, and then you have the alternative refrigerants, and you have, the greens are the A1, which is the non-toxic, non-flammable classification by ASHRAE 34. Then you have the orange is the A2L, the mildly flammable classification. And then you have the red, which is the A3, the flammable refrigerant. And by the way, this program is not just about HFOs. Of course, the majority of those refrigerants, alternative refrigerants, are HFOs or blends of HFOs and HFCs. But we are also, this program is also open to hydrocarbons, for example, such as azure-butane or propane. Same thing here for 404A. This is a list of alternative refrigerant compared to baseline 404A. And here the slide lists the 410A alternative refrigerants. Most of the 410A alternatives are of the A2L classification. In fact, finally, the R22 alternatives as well. Now, this slide shows the refrigerant with respect to the GWP values. As you can see, there's a very wide spread of GWP values. By the way, we did not purposely define what low GWP means. For us, low GWP means significantly lower GWP than the baseline refrigerants. Like the 404A, for example, which has a GWP of 3900, 1400 is considered low compared to that baseline value. So again, I mean, we purposely did not go into defining what it is, and this is something that the decision of what load means, is still being debated today. So overview, we are conducting the testing. We have 6 refrigerant producers who have supplied about 38 refrigerant candidates, and we are testing those refrigerants in a variety of applications: air conditioner, heat pumps, water source, VRF system, unitary, and so on, chillers, refrigeration application, and transport, as well as bus air conditioning. So in terms of the tests being conducted, there are typically 3 tests being done. First is compressor calorimetry testing. Then we have system dropping test, which in this particular case we allow only minor modifications to the system. And then you have a soft-optimized test where the system can be modified for the alternative refrigerant using, however, standard production line components. For example, you could also change the heat transfer areas let's say, the condenser or the evaporator, but you have to keep the total heat transfer area the same as the baseline unit that you're comparing it. Okay, so that is a fair comparison. So below that you have the number of tests, the number of candidates being tested for each of those 3 tests that I've just explained. The current status, the testing is near completion. This is the first round of testing, and so far we have 39 reports that were submitted. We have approved 26 of them as of now. 22 are already available on our website for the public to download. And then, as I said, as we move along, there'll be many more available, and hopefully by the end of the year, everything will be available for download on our website. So I'm not going to go through the results. As I said, those reports are available. You can go through them, but just to give you an idea of the kind of results we are getting out of the program, I'm going to show just two charts here to give you an idea of what kind of results we are getting. In this particular case here on the slide, you're looking at residential heat pump in cooling mode when we've tested 32, R32, and blend of 32 and 52A. And you can see the relative efficiency performance, COP performance, as well as the capacity with respect, in this case, to 410A. And for this particular heat pump testing, the reports that can be looked at are the one listed on the slide, report number 3, 4, 5. And those reports, as I said, are already available on our website. The heating mode, some kind of results, and again, this is relative to 410A in this case. In this case, the heating performance of heat pump HSPF is shown on this chart as well as this here for cooling. HSPF is the heating seasonal performance factor that is being used in the U.S. for rating heat pumps and heating mode, and here seasonal energy efficiency ratio used to rate residential heat pumps and air conditioners in the U.S. Chillers, the same kind of thing. In this case, water-cooled chillers, with respect to the baseline being here 134A, and in this case you have the refrigerants at the bottom. RM, so 42A, and so on. And you can see the relative performance of COP as well as the capacity with respect to one. The intent here is not to review the results in details. You can look at the reports and study the results there. In this case, now consider with respect to R22, and again, the refrigerants at the bottom that have been tested for that particular chiller are shown. Now, where we are, what are the next steps? Okay, so as I said, we are getting results. The results are being posted on our website. Hopefully by the end of the year, at least the first round of testing will be completed and everything will be available. We have planned a conference in January of next year in New York City, just before the HR Expo, where we will be presenting all the results of the program. That conference is open to the public, so you're more than welcome to participate. If you want more information about the conference, please look up on our website. You have the information and how to register for the conference. It's going to be a one-day conference. We are also planning a second round of testing for this program that will start in the fall of this year, and the testing will focus on high ambient conditions because the first round of testing was mostly focusing on the typical 35 degrees C outdoor condition. And although we had some results on higher ambient temperatures, that was not a requirement. For the second round of testing, we're going to be encouraging testing companies to test at high ambient conditions that we can see in different parts of the world. And also, we're going to be testing additional refrigerants as well. And that second round will start, as I said, in the fall of this year. So, in summary, this is an ongoing effort to identify low-GWP refrigerants. We have about 38 candidates for the first round. There'll be more in the second round of testing. And the intent is to evaluate those candidates and present their performance in a consistent manner. We will not prioritize those refrigerants. That's not the intent of the program. The intent is just to present the results and then to have industry make decisions on their own, manufacturers on their own, what is more appropriate. We have 22 test reports available to the public to download, and this at the bottom of the slide you have the link where those reports are available. If you don't have time to write it down, you can do a quick search on our website and find the appropriate page where you can download those reports. So I would like to acknowledge those who are participating in this program, and companies are listed, the U.S. companies as well as the international companies and the refrigerant suppliers that have provided the refrigerants, most of the refrigerants that were tested in this program. And I believe that's it. Thank you very much.
Thank you, Dr. Omran, for your presentation and for all the details. And if possible, also, I would like to have the link for the publications you mentioned, so you can make them also available on the webinar's webpage for all the participants as a reference as well. And now I would like to invite the facilitator, Ayman El-Salouni, can address the questions received from the participants.
Thank you so much, Samira.
Okay.
Thank you, Samira. And I would like to thank all the panelists for the excellent presentation and for maintaining the time of the presentations. I'd like to thank also all the participants joined us from the beginning or during the webinar. We have more than 50 participants with us. We received a few questions that I'm going to share with the panelists for their input. And I can keep my comments to a later stage, and we'll try to conclude within 10 to 15 minutes maximum, understanding that some of you may already stay longer than we already planned the 90 minutes of the webinar. The first question we received was from Mr. Divya Kumar, Emergent Ventures in India, and he has a very simple question about whether we have some basic information about the unit cost. I think he's mentioned equipment that's using HFOs, expected or approximate compared to the conventional type, I guess. And I would like to ask maybe the industry panelists or Dr. Claudic if they can provide some answers or clarification to this question.
This is Barbara Miner. We don't, because these products are mostly still developmental and there's no commercial equipment available yet, there's no the total cost of ownership of a system. One thing you pointed out was the ease of transition in that you should be able, in many cases, to use current equipment designs when you transition to the HFOs or HFO blends, and so that will significantly reduce the transition cost. And when you look at total cost of ownership over the equipment life, we believe that HFOs and their blends would be very attractive options.
Thank you so much, Ms. Miller. Any other comments from the panelists or intervention?
Well, this is Karim with HRI. Let's second what Laura just said. I mean, it's going to be, right now, it's too early to predict the cost, but I think the intent here is to come up with alternatives that could be easily transitioned into existing component that exists already. So.
Thank you, Dr. Amran. I cannot agree more with your point of view and with Ms. Mena as well. If you allow me, I can move directly to the second question, which is look more specific, and maybe you can provide any of the panelists a reply to it, which is about the revision of the ISO 5149 standard and the EN 378, which are still in a barrier to develop the use of A2L refrigerants. Any update on the development of both standards, the ISO 5149 and the EN 378?
Well, this is Tom Leck, and I can address that to some extent. The ISO 5149 and the EN 378 are still work in progress. I think the international working groups that are working on those are working to develop workable standards, specifically with regards to the ISO standard. As you're aware, the balloting that occurred in 2012 did not approve the standards, and so as a result, the working groups working on the standards have worked to address the questions and comments, particularly the negative comments around those, have made some modifications, and a revised or a new vote is being prepared for the revised standards. So I don't know if it should be the results of the revised balloting should be available. And the EN 378 may take a little bit longer. I think that it's addressing some very difficult questions about safety and use and flammability.
Okay. Any more addition to what Dr. Leck introduced?
This is Mark Sachs. I echo what Tom has just said. My understanding is that ISO 5149 should go out for ballot again hopefully later this year. We should know the results. I don't know if Dennis has anything on EN 373.
No, I have nothing. I think one of the key points for the future is to have a quick update of the refrigerant list, because EN 378 is currently behind H34. But I have nothing new on EN.
Okay. Thank you, Dr. Dennis. I would like to move to the third question, which is coming from Mr. Kelson Capers, and this time the government side, the Office of Environment and Emergency Management, the Federal State of Micronesia. And the question is about the use of refrigerant suitable for the small island condition, particularly the limit islands and islands that has a climate condition which is popular with the salt space, for the concern of all similar countries and governments in most of the developing countries. I will repeat the question again if it's not clear. It's about what should be the best candidate with refrigerant for the conditions of small islands is humid and salty spray climatic conditions.
I think it's in the best interest of people from these areas to be able to use at least the designs of existing equipment as closely as possible, so it gives them the most flexibility. And I think, quite frankly, the blends offer this ability to utilize as close as possible existing equipment. So I think it does provide promise for areas such as what was mentioned to be able to use equipment without major changes to the design.
And this is Thomas Lackey-Pont. I will add to that. I agree with what Mark has said. But looking at the question, there are several questions rolled into it, and let me try to break it down. First of all, in terms of the refrigerant gas for use in that specific environment, it's a high ambient temperature environment, and the good news is that there are several new environmentally sustainable refrigerants that are being developed for that high ambient temperature environment. So some of the choices that were discussed this morning, I think, would be appropriate. But the second part for that has to do, I think, with exchangers and for the piping, and that is indeed a challenge, getting the right materials that are resistant to the salt corrosion, resistant to the harsh environment, and yet give good heat transfer in a cost-effective manner. And quite honestly, I will defer on that and leave that to equipment manufacturers to address.
Thank you so much. I think it's a very well raised point. And there's no single solution that fits in one, as Mr. Person mentioned in his question. And even for some countries, that one solution could be the answer for others, another solution could be the answer depending on the availability and the technical support that can be provided by the equipment manufacturers in this particular region or area. For the time being, I cannot see any more questions. So if there's no more questions to the panelists, I would like to take this opportunity to thank all the panelists for their valuable time, excellent presentation, insight, and information. HFOs. Yes, Samira, please.
Can we still have time to take one more question from Mark Miller from Mopia, Canada?
Sure.
Okay, so he's thanking everyone for the excellent presentation, and however, he says that one aspect was not highlighted, and that is, are there any other environmental impacts with HFOs other than their reduced, from Mark Miller from Mopia, Canada?
Okay. Thank you, Samira. I will give the floor to the panelists, whoever is interested to respond to that.
Well, this is Barbara Miner, particularly for HFO 1234YF, since it was the first HFO developed and is being introduced into the automotive industry for automotive air conditioning, which tends to be an emissive application. There has been a lot of work done to look not only at the direct GWP of 1234YF, but when it's released into the atmosphere and decomposes, what products does it break down into, and do they have a significant environmental impact? And the refrigerant has been thoroughly studied by many industry and governmental organizations to look at those breakdown products, and they have found no significant issues with the refrigerant. So I assume the other refrigerants will probably have a similar profile.
Thank you, Ms. Miner. Any more comments from the distinguished panelists? Okay, thank you so much. I'm sure that one webinar of 90 minutes or a little bit more cannot answer all the potential or the questions related to alternate technology or refrigerant. And I'm sure that this webinar can provide only a platform to start this discussion. We have all the contacts of the panelists. It will be posted. And definitely we'll have the contacts of all the participants. And we'd like to make sure that we will maintain in touch and bring more questions in the near future about the same topic or the future topics that are going to be addressed under the RefTalk series. And if I can see no more questions, I would like to thank all the panelists for their excellent presentation and for their time, particularly those who offered to be a little bit early at their end at the US side to join the presentation and the webinar. And I would like to bring the floor, as well as I would like also to thank all the participants for joining us during the webinar. And we look forward to see you in the future webinars. And we hope that this webinar was up to the level of your expectations. And I would like to give the floor back to Samira to close this webinar session. Thank you.
Thank you, Ayman. I would like also to thank all the panelists on behalf of UNEP OzonAction and all the participants for your time and interest. Also, let me take just one moment to inform you that you will receive by email a link to the information related to our today's webinar. We will shortly make it available on the OzonAction website. Also, we received some other questions that due to the time we were not able to address during the session. However, if you are interested, you can still send me the question by email and we make sure that you will get the response. With this, we hope that you found this webinar of interest to you, and we would appreciate receiving your feedback to help us improve our services, including your suggestions for topics and or potential speakers. And as my colleague Ayman informed you, this webinar session was the number 2 of this series, and we'll get back to you soon for the next sessions on different topics. Thank you so much. The webinar is over now.